Okay, everyone. This is the second video of my online video lecture for the holiday break. And this video, I'm going to talk about the differential or derivative of multivariable function in full generality. And also, I'm going to talk about higher order derivatives and differentials of multivariable function. And lastly, I'm going to talk about the project topic 5 about visualizing heat map. And also on the long way, we're going to talk about polar forms and spherical coordinates and also Laplacian and so on. So there are lots of things to cover, so I'm not sure whether I can fit these all topics in 1.5 hours. So if I can't, maybe I can split into another lecture and give a offline lecture the rest of the parts. Okay, so let me give a definition. Start with a definition of derivative and differentials. So here I'm going to assume that my function is most general type of differential function, multivariable function. So let this f be a function and let's call each of the coordinate function in a special symbol. So let's call x1 to xn to be the independent variables, and let's call y1, ym to be the dependent variable. And as you all know, I mean, I'm making another definition. Again, I'm repeating the definition again. So when you say a function f is a multivariable function, that means each of the dependent variable is another function, another type of function, which is the real valued function, which depends on the n variables, which is same as the original function. So, if so now we have these functions. So let's say and okay, so for each j where j is running from 1 to m, let say yj, the value of j's value of the output of the function f is determined by the function called fj, and this function takes the same number of input value as the original function f, and it is n variable function of real valued. Okay, and then the definition about differentiability first. We say the original function f is differentiable at the point P, where the coordinate of P is given by constant numbers a1 up to an, if we have the following identity. So I'm going to write down this. So we have so here, since I can write down the coordinates of two points x and p, but because it's gonna make my notation long and complicated, so I'm going to assume that x represents the n-dimensional points whose coordinates are x1 to xn, and here the numerator, this is the limit where x goes to p. That means each coordinate x1 to xn is approaching to a1 and an respectively, and the limit is about the ratio, but actually you will see that it's not really about the ratio of numbers. But let me finish writing down all this. So we have xn minus an square and square root. Okay, so it's a long expression. And on the top, what we are going to do is we have f of x1 xn minus f of a1 an and minus this. So dfa1an times the x1 minus a1 up to xn minus an, okay, is equals to 0. So we say f, again, let me state the sentence again. So we say f is differentiable if this is true. So this is an equation. It says the limit on the right-hand side must be equal. So it's a statement. It's an equation, right? So I'm not saying this is a definition. It's just a statement. If this statement is true, then we say f is differentiable. What does it say? So it says there's something above in the numerator on the ratio and something on the below. So the below is a number. So it's a square sum square root. And so it's a number. And on the top, it's something weird, right? So I have a value of function. Take a subtraction of these values. And I have another subtraction as some kind of multiplication between whatever this is with n by 1 matrix. So I need to clarify this. So here, these two values, which is a value of function, is in principle m-dimensional points, right? It's an m-dimensional point. If you have an m-dimensional point, if you have any points, let's say if you have one-dimensional points, then even so, you cannot take subtraction because point is geometric object. You cannot make a subtraction between two geometric objects. But you can see the one-dimensional points as just a number on a real line. So you can say you can subtract two numbers. But here, we're assuming that this is not a one-dimensional point. M is something, could be bigger than 1. So how can you take subtraction between two m-dimensional points? So here we are talking about m-dimensional points as m-dimensional vectors. So we are taking these points as if it's a position vectors. So then we can take subtraction. So actually we are taking a difference between 2 points in m-dimensional space. And okay, so now we got something meaningful here. So we can now take subtraction. So what does that mean? That we take m-dimensional vectors in here and then subtract something that is result of two multiplication of two things. One is matrix and the other, I don't know what is. So if you want to make sense of these multiplication, here is matrix multiplication. This must be either matrix or number, right? Because anything you can multiply on matrix is either matrix or number. There's no other thing. So here we assume that this is m by n matrix. Okay? So this one is n by 1 matrix. So what happens when you multiply m by n matrix, which is represented as this one, with n by 1 matrix? You get m by 1 matrix, m by 1 matrix. So as a result, when you take the multiplication, so this thing here is matrix multiplication. This whole thing is m by 1 matrix, right? But how can you take subtraction between m-dimensional vectors and m by 1 matrix? Because you can see the m by 1 matrix as if it's a m-dimensional vectors. So we see the m by 1 matrix as m-dimensional vectors. Okay? So then now it makes sense. Whatever we do on the numerator of the limit is it's about vectors. Okay? So the result, the whole thing on the top is m-dimensional vector. And we take division by scalar number, which means that we are taking a multiplication of 1 over of this number, right, to the m-dimensional vector. And we are asking that the limit of that vector to be 0. Okay, so if the limit of vector is something, then that something must be the 0. So we have 0 vector here. So this means it's a 0 vector. It's m-dimensional 0 vector. So we say a function is differentiable, the multivariable function is differentiable if you can find the limit of vector given by this formula is a zero vector. So, and it's not over. The fa1 to an is given by, as I said, it's n by n matrix. How this is defined? So it's defined in the following way. So there are how many columns? N columns. And how many rows? There are m rows. So each row is about the function fj. So in the first row, it's about f1. So in the first column of first row, I'm taking the partial derivative of f1 with the variable x1. And I'm computing the partial derivative at p. So actually, I'm taking a partial differential at p. So p, again, is a fixed point with coordinates is a1 to an. Now, how about the second coordinates, second column here? So I'm taking a partial derivative of f1 with variable x2 at p, and so on. So at the end, I get the partial derivative of xm at p. So that's the first row. And I do the second row with the f2, and until I get to the last row, which is about fm. And the last row, I'm taking a partial derivative. And at last of last, I get partial derivative of fm with variable xn. Okay, so here, this is the coordinates. This is the entry of this m by n matrix. I'm multiplying this m by n matrix with n by 1 matrix to get m by 1 matrix as m-dimensional vector and put it into the numerator and see if the limit goes to 0. So this thing, m by 1 matrix, is called the differential of the function at the point P. Okay, so you have to remember this definition. You have to remember the full definition. Just memorize it, and keep memorizing it until you find out the real meaning. So once you find the real meaning, you're never gonna forget. But the first thing you have to do is just try to memorize this. So again, we're talking about the differentiability first, and then this differentiability is coming with the definition of derivative or differential using of this notation, and it is matrix. Okay, so you can pause the video and then just take the note or just try to memorize this. I'm gonna erase it and then give more explanation about this. So let me give a specialized definition, specialized version of definition here. So here, let's suppose that my function is real valued function. So it only takes n independent variable, but there's only one independent variable. So this is differentiable at p, which is a1 up to an, if 0 is equals to x goes to p, and denominator is same, a1 square xn an square, but the numerator is now simple, fx minus fp minus fx1 p x1 minus a1 up to f xn p xn minus an is 0. So you can see this definition is just a special case of the general definition I just gave you. because you only have one dependent variable, everything can be just one dimension, right? So your function value is the real number. You can call it one-dimensional point or one-dimensional vector. You can subtract another value here, and also these are all values. And be careful that these are numbers, not formula. It's just indicate that it's a partial differential at point P with respect to the corresponding variables, and the denominator is also the value, but that's the same thing as the original definition here. And because it's a ratio between the number and number, it must be zero whenever, whatever that is, that when you take the limit, it must be number. Okay, so that's one thing, and let me give a definition example here. So let's say my function, so if I give you a two-variable function, that's exactly the same definition we just gave in the previous video. So let me give a three-variable function as an example. So let's call exponential xy plus z squared. And let's call it p is 0, 0, 1, right? And I want to see whether this is differentiable. I think it's hard to find a differentiable, but I want to see I want to see how the equation in the definition above here formulates for this specific example. So let's see, what is it? First of all, I have f of p equals to, plug in this number, I get 2. And what is fx? So here, instead of x1, x2, x3, I have x, y, z as a symbol for the independent variables. So I can just call it fx1 as fx. And first find the derivative. So here, I'm taking only the elementary functions, which is polynomial and the composition of the exponential function. So these are just so nice functions. So I can just use the trick to find the partial derivative and partial differentials. So when I take the partial derivative, I can just ignore all the other variables as if it's just a constant. So I just, when I take f of x, I consider y and z to be constant. So I get y exponential x, and z squared is just constant, so it disappears when I take the differential of x. And fy, do the same thing. And fz, so in the z case, xy is constant, so x and y is just constant, so it's just 2z. So when I take p into account and take a differential, then fxp is 0, right? And fyp is also 0, and then fzp is 1. So the equation above here, it becomes 0 equal to limit of x, y, z goes to 0, 0, 1. And on the bottom, what is it? So it's x squared, y squared plus z minus 1 squared. And on the top, you have xy plus z squared as f of x. And what is fp? It's 2, so minus 2. And these two coefficients should appear here, but it's 0, so it disappears. So only that last thing survives, which is that minus 1. So it says the limit of this ratio goes to 0 when x, y, z goes to 0, 0, 1, right? So it's the same thing. It's the same thing, but we cannot explain it geometrically because it's a three-dimensional function, a three-variable function. So we cannot draw the graph of this three-variable function. But what it says is the same idea. Here, we get the limit of what? The square root and function value and something else here, which is 2 plus z minus 1. So this part, which serves as this part, so if I take a parenthesis here, everything becomes positive here. So all thing here, right here inside the parenthesis, is called Lx. It's called the linear approximation of the function near P. So here, this is the same Lx. So in this case, x, y, z here. So this linear function gives you the nice approximation of value of function, original function, which is so great, so nice, so that the difference between the approximation and the real value goes much faster to 0 than the speed of x, y, z goes to the point P, 0, 0, 1. So that's what it says. equals to 0. So let me write that out here. So f y z being differentiable at P means that the linear approximation of Lx is in some sense good. Okay. All right. So let me give another example. So this is the simple case. So let me give some complicated case that we have several dependent variables to find the meaning of differentials. So here, let's say f xy goes to x squared plus y squared xy. So let's say my point P is 1, 1. So I can't draw the graph of this because we have 4 variables. I cannot draw anything on 4-dimensional space in 2-dimensional plane. But I can take imagination, and I think I can compute what the FP is, and then see what happens when I play with this DFP. Oh, sorry, just the FP, yes, not subscript. So what did I say about the differential? So this differential is a matrix. It has number of rows and number of columns. The number of rows are determined by the number of dependent variable, which is m in the general case, and number of column is dependent on the number of independent variable, which is number n. So here there are 2 independent variables and dependent variables. So the matrix is 2 by 2 matrix. So it's going to be del f1. So here you can see correctly. So here this one is f1, and this one is f2. So that's the formula that determines the first dependent variables, and this is the formula that determines the second variables. So dfp is del f1 del xp df1 del yp and del f1 del f. I'm just writing exactly the same as my definition here. It's f2 and p. 2 by 2 matrix here. And what do I have to do to find out each value? So yeah, it's a direction derivative or partial derivative. I just need to take the partial derivative. So look at f1 here. When I take the partial derivative, it's 2x, right? So it's not 2x. The answer is not 2x because I'm taking a partial differential at the point P. So I'm taking partial differential at P. So I need to plug the value of P into the formula of derivative. So when I take the partial derivative of f1 in terms of x, it's 2x because y is considered as if it's constant. So it's 2x and x is 1, so I get 2. And how about here? I get the same formula, but I'm taking partial derivative in terms of y, so it's 2y. So I plug in 1 here, so it's also 2. So how about here? So I'm taking partial derivative of xy in terms of x. So y is considered as constant, so it's just y. So y is 1. And here again, the same thing happens, so it's 1. So this 2 by 2 matrix is the derivative of the function at the point P. So now you might wonder, what does it mean? What does this derivative actually means? So here's the meaning. So whatever we do for derivative, derivative or differential, so this what we do when we find derivative or differential is the map that assigns the change of input, a change of input to the change of output. So what do you mean by change of input? So here is the picture. Here's x and y, and here's the map. And let's call this as y1 and y2, or you can call it f1, f2 if you want to. So let's call it f1, f2. Well, let's call it y1, y2, because f1 usually represents the formula and not variable. y1, y2. Okay, so that's my function. So I'm looking at the point 1, 1 in my domain, and I can move my point 1, 1 in any direction I want. So for example, I take u vector and I want to change my 1.1 from 1.1 by u. So my new point, let's say that if this is u, then my new point x will be p plus u, right? So let's call it p here. So then, my 1, 1, when xy is 1 and 1, maps to 2, 1, right? So y1 is 2 and y2 is 1. So 2, 1. So it was right here. The value of function was here. The value is now not a number, but it's a point. So when I have a stationary point at my domain, 1, 1, then my value is also stationary. It's not moving from 2, 1. But as soon as I move my point from 1.1 to a certain degree by a certain angle or a certain direction, my value of the function, the point on the codomain space also changes, right? So I want to change approximately in which direction and in which speed does this 2.1 moving. That's my concern. So let's call V, okay? Let's call it V. So so this is my FP, and the point that is moving will be FP plus V, right? So I want to see V. I want to see what approximately this V is. So there is the actual change, actual point that is affected, that is the result of changing a point P. So that is f of x, which is f of P plus U. But I want to see the difference of these actual result, approximately how much is this actual result differ from the original value fp. So my v will not accurately estimate my actual change of my function, but it could be a good approximation. If my change of x from p is small enough, then you see the point might change not with a line, but it change with some kind of curve. But if I have a smaller and smaller change, this change might almost follow the linear line. So I can say v is almost equals to f of p plus u minus f of p. So that's what I want. So how different is actual change from the real value or original value of the function? So that's my concern. So the derivative, what does derivative do is that it relates the change of inputs to the change of outputs. So if you want to see the change of output, approximate change of output, which is given by vector v, simply multiply the derivative of the function at p. So this v is the result of multiplying the vector to the matrix, which is given by the derivative of the function p of f at p. So that's the meaning of the derivative. Derivative assigns the change of inputs to the change of outputs. Okay, and the way you can find out the approximate change of our output is by multiplying your derivative to your change of input, which is given by the vector or the matrix. So here's the mean. So here I have a meaning here. I have an example here. So let me give you an example. So if p, which is 1, 1, is changing instantaneously by u, which is 1, so this is a vector, so I need a vector notation, 1, 2, then the value of function, which is fp originally, this was 2, 1, is changing approximately by v vector, which is given by the differential, which is 2 by 2 matrix, 2, 2, 1, 1, times the u vectors. So here, vector is not a matrix, but we have to convert the matrix vector into matrix in order to get the matrix multiplication. So the way we convert the vector into matrix is we always use the column vector. So 1, 2, like this. So we have a single column. So then what is it? It's 6, 3, right? So v is actually 6, 3. The coordinate of vector v is 6, 3. So if you're moving in a direction of 1, 2 in this direction, let's say that's u, then we know that if 1, 1 is instantly moving in that direction with that speed, then we know that the point 2, 1 in the codomain space is moving with 6.3 velocity from 2, 1. So that's the meaning of the differential. That's that's the role of a differential. The function maps the point to point, but differential maps the movement to the movement, instant movement to instant movement. Okay, so let me give a different way of looking at this, and this is very important also in when you want to learn about when you learn about the physics and the mechanics. This point of view is very important. So I'm going to repeat many times what I just said again. So let's think about situation here. So x1 to xn here. So here is your function. So I'm assuming that there are other x's, but I can't draw it. So I just made the first and last coordinates here. And let's say this is y1 to ym. Okay. So what we do is we take a point P, which is A1 up to AN, and we took image of that point to, let's say, B1 to BM, right? And what I said is the function maps point to point, but differential maps vector to vector. So these vectors represent the changes of the points in domain and codomain space. So P moves in U direction, then instantly, okay, infinitesimally small amount of time. If P moves in direction of U and with the speed of U, then Fp is moving in some direction with the some velocity. So let's call it V. So then V is mapped by the differential of that function P with U, with this formula. So here, this is M by N matrix, and this is n-dimensional vector as n by 1 matrix, and this is m-dimensional vector as m by 1 matrix. So now everything makes sense. So it's about the matrix multiplication. So I can say the same thing with a partial derivative symbol. So actually this comes after when you naturally after you learn about the chain rule, but I want to make sure that this is also makes sense. So let's say you're moving in a special direction. So if you're moving with this very special direction, which is 1, 0, 0, okay? So what are we looking at? We're looking at the change of x1 coordinates from A1 and take the rest of the coordinates fixed, right? So I'm just changing the x1 coordinates and see how all the coordinates in the outputs are changing. So you see y1 is changing and ym is changing. That's true, but the change is only the result of the first coordinates in the independent variable, which is x1. So we are actually looking at the velocity of, the partial derivative of the y1 up to ym coordinates in terms of x1. So when I have this, then the v, which is the change of the value of function, is given by delta f1 delta x1 up to delta fm delta x1, right? So let's make it into a vector notation, vector, okay? And now I'm going to do something very special here. So instead of writing this u and v in terms of their vector notation with the bracket symbol here, I'm going to give a name for this as del x1. So why del x1? Because it has only 1 on the first coordinate and 0 everywhere. So actually it comes from 1 times del x1 plus 0 times del x2 plus up to 0 times del xn. So rest of the sum is vanishing. Only del x1 remains. So that's why I call it del x1. So then, what do I have? So I have m-dimensional vectors. So I can split this up into sum of m different vectors whose coordinates are only non-zero at one place and rest of them are 0, and 0 up to 0 and del fm del x1, right? And then for each case, you can make this as a scalar multiple of the unit vector 1, 0, 0 times del fx1 del x1, and this one too. You can make 1 here, and it's scalar multiple of, it's x. Yes, fm, sorry. So fm over x1. Yeah. So like this one. And I will do the same thing to replace these vectors with a partial derivative symbol. So I can say f1 del x1 times. So you have only 1 on the first coordinate. And as I said, it's when you have 1 here, it means that it's 1, 0. There are coefficients of these partial derivatives here. But here we have the vector represents the change of the y space, not x space. So the change represented by this vector is change in y1 vector or y1 coordinates. So it's del y1, not x1, because the space is totally different from this one. So we are talking about the v. So del y1 is right. And then del fm del x1 del ym. Okay? So if it don't make sense, if you can't understand this, if intuitively it doesn't make sense, then just take it as a definition. So in physics and many even for many mathematical contexts, they use, instead of vector notation, they use this as a notation of vector. So just take it as a notation. So what we can do is, so as I said, this u and v are related. But in some sense, this v is determined by u, and maybe u, and also u makes the result of v. So I can just say, if I wanted to make this change, then this is the only cause that made this change. So I can't just equate these two things, because whatever we do, there is, of course, the connection between these two spaces through the special function called f, but we are actually looking at the changes in two different spaces, and they are connected, they are related. So it doesn't matter whether we see the difference in the domain, this space or that space, because they are connected. So I want to say that these are the same thing each other because of these settings. So I want to say del x1, which is the change of p originally, is actually intrinsically the same as the changes in the space of y. So del f1 del x1 del del x y1 up to del fn del x1 del del ym. So I think that some rigorous mathematicians hate this way of writing and saying it, because this is actually the chain rule, not the one that you can explain without a proof of the chain rule. But I want you to convince that this is not a mathematical formula. This conveys the meaning of the partial derivative and also the meaning of the differentials. Because all we have been using for deriving this equality is nothing but the differential, nothing but the meaning of differential, which relates the difference of P and difference of Fp here. So all I'm saying as a leap of faith is that I want to see the changes in these two spaces are intrinsically the same thing. Of course, the numbers are different. Of course, the points are different. Of course, the spaces are different. But intrinsically, there's no difference seeing the changes in here and there, because one is derived from another. So I can say this. So you can also give a meaning to this equation, saying that if you change your point P in the domain space with the direction of x1, then it causes the changes of your codomain space of corresponding point by each coordinates by this amount, right? So in y1 coordinate, it changes by this much, and ym coordinate changes by this much, right? So this equation actually makes sense. So I can do this with different vectors. Instead of 1, 0, 0, I can take u to be 0, 1, 0 here. That means I'm taking del del x2 instead. So in that case, I'm changing the x2 instead of x1 and do the same thing. But then in that case, I'm taking the partial derivative with respect to x2 instead of x1. So if I keep doing this until I get to the xn, then what I'm doing here is I get the more equations. Actually, I get m equations, up to, so the second equation will be given like del del x2 is f1 x2 del del y1 fm x2 del del ym, and so on. The last one is del del xn, del f1, del xn, del del y1 plus del fm, del x n, del del y m. Okay. Okay. So this is actually the same. I mean, if you learn up until the end, then you will understand that this is actually the same as the meaning of the differential. This equation exactly conveys the meaning of the differential of the multivariable function. But for now, let's count this as a separate equation from the definition of differential. And let me give an example how to use these equations. So let's say my f is a multivariable function, two function, so given by 2x plus y and minus x plus y, and my point P is 1, 2. So let's find all possible partial differentials at the point. So this is f1, so this is f2. Actually, it doesn't depend on the p because it's all linear, but let's find it anyway. So f1 x1 at p, what is it? Sorry, x here. Oh, so if you're confused, I don't want you to be confused. So let me change the notations. instead of xy, let's use x1 and x2. So in that case, you might find it easier to apply these theorems, equations. 1, 2, 1, x2. So what is f1, x1? So I'm taking partial derivative only this part. This is 2. And what is f2x1 p? So this equation has x1 here, so it's -1. And f1 x2, so it's +1. And f2 x2 p is also 1, right? So I can translate this equation as follows. So del that x1 is 2 times del that y1 plus minus del y2, and del that x2 is same as del y1 plus del y2. Okay, so using these coefficients here, so I have this. So think about the geometric situation. I have function that maps x1, x2 space to y1, y2 space. So we have 1, 2 right here. And at 1, 2, what's the image? It's 4, 1, right? So 4, 1. And I want to know if what happens when I move my 1.2 in direction of 1, 1. I want to know how fast, in what direction, in what speed does 4.1 is moving in y space, right? So that's what is not known. All right, so how do you write down, again, as an example, how do you write down the movement of this point, 1, 1, in terms of delta x and delta 2? Because 1, it's 1, 0 plus 0, 1. So we have 1 unit of movement in 1, 0 direction. So there are 1 delta x1. And also you're changing x2 by 1 unit of length. So you have delta x2. So here we have delta x1 plus delta x2 as my change of x, right? Change of p. So then I'm going to replace this. I'm going to apply this. So delta x1 is causing my change in the y space as this much, right? So this is 2 times delta y1 minus delta y2. And delta x2 is causing my change of this image point by this much. So plus delta y1 and delta y2. So let's combine the terms here. We have 3 times delta y1 minus 2 plus 1, so it's minus delta y2. So this is my v. This is my v, right? So if you translate it as a coordinate, then it's moving by 3 in the y1 direction, and it's moving by -1 in the y2 direction. So actually going down, but sorry. So anyway, so using this notation, you can easily find out how much the image point moving according to the movement of the input points, right? So there's an upshot to this kind of notation. So if you use this notation, you can easily understand what happens on the polar coordinates and spherical coordinates. So let me give an example. Let me give a definition of polar coordinates and spherical coordinates, and let's try to make application of this idea here. So remember this, because I'm going to erase it. So definition, the polar coordinates of the Cartesian coordinate xy is r, theta, where x is r cosine theta and y is r sine theta. So whatever r theta satisfies this two equation is called the polar coordinates of xy. So here's an example. So if your point xy as the Cartesian coordinate is 1, 1, then the polar coordinates of this is, okay, so you can draw the picture. It's 1, 1. So you can see that by looking at this formula, so if you have a radius r circle with the angle theta, then that's the x-coordinates, right? So this is theta and this length is r. So you can say, okay, so what's the length between the segment joining the origin to 1, 1? So it's square root of 2. So r is square root of 2, which is the first coordinates. And what is the angle? It's 45 degrees. So it's a pi over 4. But that's not the entire way to write down the polar coordinates, because you can have 2 pi degree, I mean, you can have one more rotation, right? So you can also get the same Cartesian coordinate by another polar coordinate, square root of 2, and adding 2 pi or more. Or, it's more interesting, usually we assume that r is positive, but you can have a minus r, right? So if you have a minus r, you're actually on the opposite side. You can get a pi degree more to get the same thing, but that's not common way of, traditional way of doing it, so I'm not going to write it. But anyway, you can, if you add 2 pi rotation, then you can get actually the infinitely many ways to write the polar coordinates of xy. So sometimes we restrict the domain range of r and theta in order to make one-to-one map, but in principle, the polar coordinates is not defined that way. So anyway, so here's the remark. The map T that sends r theta, to r cosine theta, r sine theta is called the polar transformation. Okay, so it's a transformation between polar coordinate space to Cartesian space. And we know that this is x, and we know that this is y. So now let's consider r theta as a role of x1, x2, and xy has a role of y1 and y2 in our multivariable settings. And let's try to find out what is delta r and what is delta theta. So that's why I said you have to remember the formula before we move on to this scene. So if you forgot about the formula, yeah, so if you forgot, then go back and then see the formula again. So anyway, so what is delta r? So it's x r delta x and y r delta y. So you're taking a formula of x and take a partial derivative of r, so you get cosine theta and delta x. And then, well, you take a partial derivative of y in terms of r, so you get sine theta delta y, right? So, and then, what? You take delta theta, so del x, del theta, delta x, and del y, del theta, delta y. So let's see, x partial derivative with theta gives r sine theta delta x, and here you get r cosine theta delta y, right? So what do we get? So it says that if you're moving in the r direction in your r theta space, then the corresponding movement in xy space is this much. So let's see what happens. So let's draw the picture. So here is r theta, and the translation t is mapping a point in r theta to xy. So let's say we are at r0 theta 0, whatever that number is, and that corresponds to x0 y0. So del del r means that it's moving in the r direction with the unit speed. So we are moving in this direction. That's del del r. So then it's same as moving xy, x0, y0, this amount. In x direction, you're moving by cosine theta. In y direction, you're moving in the sine theta. Right? So theta here is determined by the theta value here. So it's theta 0. So in the x coordinates, amount of movement is cosine theta 0. So this is cosine theta 0. And the y direction, that's sine theta 0. So if you have these two combined actions, so if your x is moving in the speed of cosine theta, y is moving in the sine theta, what's the overall movement? It's moving in this direction, right? So that's your cosine theta 0 del del x plus sine theta 0 del del y, right? But do you see the angle here? Because cosine theta, sine theta, if you take that as an xy coordinates, then this point is having a direction of angle theta 0. So that's right here, theta 0. So you see, what's the speed of movement in this case? So theta, cosine theta, and sine theta is the point on the unit circle. So the arrow that is pointing this direction is pointing to the boundary points of a unit circle. So the length of the arrow is 1. So when you're moving your point, it's a unit speed in r direction. You're just increasing the radius of the point from the origin. That's exactly what this is. So if you elongate this line, if you extend the line from here, and it will hit the origin, and the angle is also theta 0. So you're moving in this direction, right? The same thing happens when you're moving the other direction. So let's say we are moving in this direction. So that means you're changing your theta in the unit speed. So the theta is in radian, so you're moving in radian direction, increasing. So it says your x coordinate and y coordinates are changing this much. So x coordinates are actually decreasing and y coordinates are increasing. So actually it depends on what your theta 0 was, because here what happens is, so now your movement is r0 sine theta 0 in minus direction, and let's say this is r0 cosine theta 0 here, right? So now, if you have a sine and cosine, what's the direction means? So it has the size of r0. This arrow, which is the sum of these two vectors, is having a length r0. And what's the direction? So we know that the direction that connects the origin to the point is angle theta 0, and that's cosine and sine. And if you take the product between inner product between cosine theta 0, sine theta 0, and the vector of this blue part r0 sine theta 0, r0 cosine theta 0. What's the inner product? Cosine minus sine plus sine cosine with the same r0 here. It's 0, right? So the blue line is actually perpendicular to the red one. So we know that if you move your r theta in direction of theta, your point in xy coordinate and Cartesian coordinate is moving in a perpendicular direction to the line connecting the point and the origin. So it means that it's moving along the tangent direction of a circle. So you're actually changing the theta only. So the why we have r theta, because if you have a larger r theta, your movement is actually faster because you want the constant change of your angle. Your angular velocity is constant and it's speed of 1. But actual movement in xy plane depends on how far your point is at from the origin, which means that how large the radius is that your point is moving on. So this kind of notation is very useful to interpret actual movement in the two different spaces. So that's what I wanted to introduce. And one more thing I want to introduce. So I think I cannot go through the project part, but I really want to introduce this one. It's about higher order derivatives. So let's call it definition here. So whenever you have a multivariable function, let's say this function maps Rn to Rm, so it has n independent variable and m dependent variable, then you can say that there is m by n matrix whose entries are all functions, not numbers. Okay, so each function has given by the partial derivative x1 up to f1 delta xn and fm x1 fm xn. So you can see that there is m row and n column, but each entry is not numbered anymore because we want to express that as a formula in terms of x1 to xn. So this is called the derivative of the function f. Okay, but even though it takes the form of matrix, it's actually another type of function, right? So del f takes the input value of n independent variables, right? It still have the formula in terms of x1 to xn. So there's nothing more variable required to compute the value of df, derivative here. So the input is always n-dimensional vector. But how many outputs are there? So output itself is a matrix, and matrix it's a two-dimensional array, but it's just array list of values. How many values do you have? Has m times n values. So you can consider this as another multivariable function that sends n-dimensional vector, n-dimensional point to nm-dimensional points. So because I can just linearize this array of numbers into one-dimensional vectors and call it as a n-dimensional point, right? So it's just another multivariable function. So once you have this function, you can just replace the name for this, and then you can get another derivative. So what's the derivative? Again, so what we do is we simply take each of the function, coordinate function, as a new function, which determines the corresponding value, dependent values, and take the partial derivatives, right? So if you want to, I mean, it actually becomes, in some sense, three-dimensional matrix because we already have two-dimensional vectors, a two-dimensional array of numbers. Then now you want to add another dimension to take the partial derivative of these functions. So let's say, I'm not sure whether I can make a nice picture out of it, but so they're assuming that there is a matrix stacked together in a three dimension, and the foremost one is one that has the coordinates all taken partial derivative of each of these. So let's say I want to take partial derivative in terms of x of the first coordinate here, coordinate function here, and partial derivative x1 of this one part. So here lx n here, and del x1, del f1, del x m here 1, del x1, del fm, del xn here. Okay, so then that's the first step. Like you have to take the first partial derivative, and the second part, and the second and third, and up to the last one. The last one is the partial derivative with respect to xn. So f1, x1, and so on. So again here. So you can imagine that there is how many nmn number of elements in your big space, right? So you can take the second partial derivative and second derivative itself too, right? But what requires to find then you can take the third derivative, fourth derivative, but what requires to get this higher derivative is that you need to know how to take the partial derivative of each functions, right? So partial derivatives, higher order partial derivatives. So here's the definition again. The nth order partial derivative is the partial derivative, or it could be a differential, depends. Partial derivative or differential of the n minus first order partial derivative. So what does that mean? So let's say f of x, y is exponential x plus 2y, right? So then I want to find out partial derivative of x of partial derivative of y. Okay, so I want to find the partial derivative of y, and then take that as a new function, and then take a partial derivative of x again. So what is partial derivative of this formula in terms of y? So I take x as a constant, so we get 2 exponential x plus 2y. And then I take the partial derivative in terms of x, again, for this one. So as if this is a new function. So therefore, partial derivative of y is 2 exponential x plus 2y. The same thing here. So you can get the higher order partial derivative, then you can get the higher order derivative of the function. So where do we use higher order derivative? So there are many places to use it. First, we can use higher order derivative to find the Taylor series of a multivariable function. And second, we can also use it for finding the so we can use it for harmonic functions and Laplacians and so on in the physical sense. And another way of using the use of the higher order derivative is finding the optimization. So optimizing functions, find the local maximum, local minimum, which will be covered in the chapter 6. So I think I'm going to wrap up here. So things that we haven't covered here is so things that we haven't covered there is some examples of higher order derivative, and also some nice properties of higher order derivative, and also some counterexample that doesn't that gives a warning when you take a partial derivative many times. And also we haven't covered about the conformal mapping and harmonic function, which has to be done in order to do the project topic 5, but I don't think we have enough time to do this. So I'm gonna explain it more after our long holiday break. So yeah, so have a nice break and see you after the break.